going to talk about the quota rule and paradoxes. So today we're going to dig into some of the drawbacks of each of the 5 methods of apportionment we've studied. So one of the most basic ways to judge the fairness of an apportionment method is by something called the quota rule. And the quota rule says that an apportionment method should give each state no fewer than its lower quota and no more than its upper quota. Right? So we should take its standard quota and either round it down or round it up. And that seems to make sense. That's really the only fair thing to do. So for example, if a state's standard quota, that is their exact fair share, right, is 138.29, the only fair thing is to give them 138 or 139 seats, because you can't give out the 0.29, so you either give 138 or 139. If we give fewer than 138, we call that a lower quota violation. And if we give more than 139, we call that an upper quota violation. So let's think about Hamilton's method for a second, how Hamilton's method works. Remember, with Hamilton's method, you get the standard quotas, you round everything down, and then you give out the surplus seats, right? So everyone's either going to get their lower quota, that's the lowest they can get, or they might get one more than that, which would be their upper quota. So will Hamilton's method ever violate the quota rule? No. No. All states get at least their lower quota. Get at least their lower quota, because that's how we start. We get the standard quotas, we round everything down. Some states will get one more than their lower quota, which is their upper quota, right? If they have a big enough decimal piece, they might get one more. Some states get one more. So they get the upper quota. Okay. So Hamilton's method will never violate the quota rule. But let's revisit the example we did when we studied Jefferson's method, the same Congress of Peridor example. And I have it all done out here. We got the standard quotas, we rounded everything down, we added them up and it only came out to 246, so we made the divisor a little bit smaller, went to 49,500, got new modified quotas, rounded them down, and now that adds up to 250. Okay, so what do you notice about State B's standard quota, which is their exact fair share of seats, and what we gave them in the end? It's more than one bigger than their upper quota, right? This is an upper quota violation. Yeah. So it turns out that Jefferson's method can sometimes produce upper quota violations, only upper quota violations, and even worse, these violations consistently favor large states. So a large state is going to be the one that gets more than its fair share, bigger than its upper quota. Okay, so this is not good to consistently favor large states over small states. So this problem actually came to light in 1832. It was one of the most heated apportionment debates in U.S. history. We were using Jefferson's method, and New York standard quota was 38.59. However, they were apportioned 40 seats. So we can see that's an upper quota violation because they should get either 38 or 39. And this was a very heated debate, and this was actually the last year that Jefferson's method was used because its constitutionality was questioned. And Adams and Webster's methods were developed in response to this 1832 failure of Jefferson's method. So let's look at those two and see what happens with them. This is Adams' method in the Congress of Peridor example. We already did this example, so I just reprinted it here for you. Remember, Adams' method rounds everything up. Okay. So we get the standard quotas. I rounded everything. Oh, look, I did it wrong. 33, 139, 4, 42, 14, 20, and when I add all those together, what do I get? This would be 3 is 142, 172, 176, 178 plus 40 would be 88, 98, 08, 18, 218, right? Somebody already have it? What is it? I lost track. 252? Okay, thank you. All right, so that adds up to 252. And we said, oh, that's too big, so let's change our quota. Let's change our divisor, right? This came out too big, right? Which means I need all of these quotas to be a little bit smaller. So I'm going to divide by a bigger number, right, to make the answers come out a little bit smaller. So I'm going to divide by 50,750 this time. And I get these new quotas, modified quotas, round them all up, and now it adds up to 250. Okay, so what do you notice about State B's standard quota and final apportionment? State B's standard quota and final apportionment. Too low. This is a lower quota violation. Right. Their standard quota was 138 point something, so 138 is the lowest we should give them, but we gave them 137. So it turns out that Adams' method can sometimes produce lower quota violations, and even worse, these violations consistently favor small states, right? It takes seats away from big states, so it's biased against big states, whereas Jefferson's was biased towards big states. So we can conclude that Adams' method is no better or worse than Jefferson's. It's kind of like the exact opposite problem. And after considerable debate, there was a bill proposed to use Adams' method as our method of apportionment, but it never passed, and it was never used to apportion the House of Representatives. All right, let's take a look at Webster's method. Here's Webster's method carried out. Hopefully I did it correctly. I did not. Look. Okay, so Webster's method, let's go through and fix it. So we get the standard quotas. Those are all right. Divide everything by the standard divisor. And then rounded quotas for Webster's, you're supposed to round using the standard rounding method. So this should be 33, 139. 3 is correct. This should be 42. This should be 14, and this should be 20. And this would add up to 251, which is too big. I need to make all of my quotas a little bit smaller, so I'm going to divide by a number that's a little bit bigger. So I'm going to change to a modified divisor of 50,250. And we have solved this problem in a previous class. So I get all new standard quota, all new modified quotas. Then I round them conventionally. So 32.75, that should round up to 33. 138.02 down to 138. Okay, so it looks like I did these right. And that comes out to exactly 250. Do we have any violations of the quota rule in this particular example? No, everyone got either their lower quota or their upper quota. So it turns out that Webster's method tends to produce apportionments that are pretty close to the standard quotas, meaning either that gives the lower quota or the upper quota, but can very occasionally produce quota violations, both upper and lower. But at least these violations seem to show no bias between large states and small states. So there are occasional quota violations, but there's no bias. It doesn't consistently give the upper hand to large or small states. But surprisingly, Webster's method was short-lived in the House of Representatives. It was replaced after 1931 with the method we currently use, Huntington Hill. And given how similar Huntington Hill is to Webster's, it's no surprise that it also tends to produce apportionments that are pretty close to the standard quotas, but it also occasionally can produce quota violations, both upper and lower, and shows no bias between large and small states. So Huntington Hill seems pretty good, except that it can sometimes produce upper and lower quota violations. So it appears that Hamilton's method is the only one of the 5 that we studied that does not produce quota violations, ever. Okay. So this is a big pro for Hamilton's method. So why do you think we just don't use that one? Too simple? Maybe. But in fact, it actually has 3 really big cons, 3 really big problems that happen with Hamilton's method. When you dig into certain kinds of examples, you can have these really big problems. So I'm going to do 3 examples. Each of these examples demonstrates a big problem with Hamilton's method. So I have a small country that has 3 states, Fama, Tecos, and Ilnos, and it has a total population of 20,000, and we're giving out 200 seats in the House of Representatives. So I want you to take 5 or 6 minutes and do the apportionment under Hamilton's method. All right, so let's go through together. The first thing we have to figure out when we're doing Hamilton's method, or any of the methods really, is the standard divisor, right? Your standard divisor is always your total population divided by the number of seats, or your total population divided by the number of things you're giving out, right? So that comes out to 100. Standard divisor of 100. So then you take each state's population, divide by your standard divisor of 100, and those are your standard quotas. So 940 divided by 100 is 9.4. 9,030 divided by 100 is 90.3. 10,030 divided by 100 is 100.3. Add those up, you should get exactly 200. Now I take my lower quotas. I round everything down, and I get 9, 90, 100, and that adds up to 199, which is too few, right? So in every other method, we would think about changing the divisor, but in Hamilton's method, we decide we give out those extra seats to whoever has the biggest decimal part, right? So my decimal parts, let's see, I might split this into 2 columns to help me. So 0.4, 0.3, 0.2, those are, I'm sorry, that's 0.3. 0.4, 0.3, 0.3, those are my decimal pieces. Which one of those is the biggest? 0.4, so they get my 1 extra seat. Everyone else gets nothing. So 9 plus my 1 extra seat is an apportionment of 10. Everyone else just gets their lower quota, 90, 100, total of 200. So this is my final apportionment, 10, 90, 100. Okay, now imagine, overnight, the number of seats increased to 201. But nothing else changes. The populations all stay the same, but I change the number of seats to 201. Take 5 or 6 minutes, recalculate the apportionment using 201 seats. All right, so let's just go through this together. We need a new standard divisor, right? If we change the number of seats, that's going to change our standard divisor, which is now 20,000 people divided by 201 seats. So I get 90.5, 99.5. We'll leave it like that. Okay, so then I'm going to take each state's population and divide by the standard divisor. 940 divided by 99.5. 9.447. And 90.75. and 100.8. When I add those up, it should come out to very close to 201. If it's not exactly 201, it's because I rounded some of those numbers as I was writing them down. Okay, so next step in Hamilton's method is to take the lower quotas. So I round everything down, and I have 9, 90, 100. That adds up to 199, which means I have 2 seats left to give out, right? Because I'm giving out 201 seats this time. So I'm going to look at the decimal pieces, 0.447, 0.75, and 0.8. Looking at my decimal pieces, which one is largest? 0.8, and which one's next largest? 0.75. So those two get the surplus seats. So Illinois, their lower quota was 100, plus they get an extra, they get 101. Tecos, 90 plus an extra is 91. And Bama gets 9, no extra. And now I have 201 seats. Okay, so compare your results from the previous one, yesterday's apportionment, right? Before we increased to 201 seats, Bama had 10, Tecos and Illinois had 90 and 100. Now there's more things to give out, right? So if we increase the number of seats, everybody should be like, ooh, maybe I'll get an extra, right? But what happened? Bama lost theirs, yeah. So Tecos and Illinois both got an extra. One of them got the one extra that when we increased to 201, but one of them took a seat away from Bama, right? So Bama is really upset, right? We took away a seat from them. Okay. And this result is an example of something called the Alabama paradox. And it happens when you increase the number of seats to be apportioned, and that causes a state to lose a seat. Okay, and this name comes from the 1882 apportionment of the House of Representatives. Here's a little summary of what was being debated. We were deciding whether we should have 299 seats or 300 seats in the House of Representatives. And with 299 seats, Alabama got 8. And with 300 seats, their apportionment went down to 7. Right? So I don't like that. And so when we increased by a seat, one of those extra seats went to Texas or Illinois, right? But then the other of the two, Texas and Illinois, kind of like stole a seat from Alabama. So this is a weird paradox that can happen with Hamilton's method. So that's one reason we turned away from Hamilton's method. This problem upset Alabama and happened a few times, so we turned away. All right, now we're going to do another example that shows another drawback of Hamilton's method. The year 2525. The 5 planets in the Utopia galaxy finally signed a peace treaty and agreed to form an intergalactic federation governed by an intergalactic Congress that has 50 seats in it. And this is a story of the 2 apportionments that broke up the federation, right? So first, use Hamilton's method to do the apportionment for 2525. And then go on to the next one. 10 years later, we do another apportionment because the populations have changed a little bit. We reapportion based on the census every 10 years and calculate the new apportionment and see if you see any weirdness, anything that would cause the federation to break up. All right, let's go through together. So first thing we need is a standard divisor, right? And you get that by doing the total population, which is 900, divided by the 50 seats, by the number of seats, and you get 18. So then we take each state's population and divide by 18, and you get by 18, right? Okay. 8.33, 4.33, 9.61, 11.3, 16.4, Okay. And then we should take lower quotas, right? And so that means round them down. So I have 8, 4, 9, 11, 16, and that adds up to 48, right? So I have 2 to give out. So who should I give them to? The 0.61 and the 0.4? Coney and Elysium. Okay, so everyone else does not get an extra, right? Just looking at the decimal pieces, give the 2 leftovers to the extras, to the largest decimal pieces, and then add lower quota plus any surplus. So we have 8, 4, 10, 11, 17 to add up to 50. So that's the apportionment everybody got? Good. Okay, so there is peace throughout the land for 10 years, right? Then there is a 2535 census. There's some small changes to some of the planet's populations. So you can see the total population has gone up a little bit to 909. And let's see what changed. Alanos was at 150 and it stayed at 150. And Beta was at 78, it stayed at 78. 173, 204, 295. 173, 204, 295. So I'm just writing down the previous year's population so we can have them to refer to. So most of them stayed the same. So Coney went up by about 8, right? Million, I think we're measuring this in. And Dugo stayed the same, and Elysium grew by 1 million. All right, so my standard divisor is going to change because my population changed. So it's now 909 divided by 50. And what's that? 18.18. Good. So then I divide each state's population by 18.18. And can somebody read them off to me? Great. That should add up to just about 50. If it's not exactly 50, it's because we might have rounded some of those numbers when we were writing them down. It should come out very close. So then lower quotas, round all these down, and I get 8, 4, 9, 11, and 16. And when I add those up, I should get 20 and 16 is 36, 40, 48. Okay. So I have 2 surplus seats to give out. Who should I give them to? Yep, Coney has the 0.95. That's really big, so they're going to get 1. And then who's the next biggest? Yeah, Beta or Beta. So then we've given out our 2. Everyone else gets nothing. Total of 2 seats to give out. And so now the final apportionment is the lower quota plus the surplus. So we have 8, 5, 10, 11, 16, 50. So let's just jot down next to that what the apportionment was 10 years ago. So we have 8, 4, 10, 11, 17. 8, 4, 10, 11, 17. Okay. So what do you think? Is anybody upset? Is anybody psyched? What's going on? Beta's upset because they lost a seat, right? But their population stayed exactly the same, right? Anybody else? Who's? Oh, Beta gained a seat. Sorry, I was reading it backwards. So Beta gained a seat, and their population stayed the same. Elysium, their population grew, and they lost a seat. So that's weird, right? Beta, their population stayed the same, and their apportionment went up. They got a whole nother seat for no good reason. whereas Elysium's population grew and they lost a seat. Not even they stayed the same, they lost a seat. And then the one who grew the most, right, Coney, went from 173 to 181. Their apportionment stayed exactly the same. Okay, so the one who grew the most, you would think, if anything, they would probably get the extra seat, but we ended up giving an extra one to someone whose population didn't grow and taking one away from one whose population did grow, and left the one whose population grew the most alone. So this is a very strange result. And it's called the population paradox. It happens when a state's population goes up, but the number of seats it is apportioned goes down. So this happened to Elysium. Elysium lost a seat even though its population went up. So we have the Alabama paradox, right? If we have more stuff to give out, sometimes that means a state loses a seat. And then we have the population paradox, where your population can grow, yet you lose a seat. Very weird stuff. All right, last big drawback of Hamilton's method. For a change of pace, we're going to use a non-political apportionment problem. We have a garbage company that serves Northtown and Southtown, and they have 100 garbage trucks. So we want to apportion them. How many garbage trucks should we send to Northtown? How many garbage trucks should we send to Southtown? Apportion them using Hamilton's method. So do that first, and then we'll come back and talk about the next thing. Okay, so let's do these two apportionments together. So we have Northtown and Southtown. Populations are 10,450 and 89,950. And that makes a total of what? Oh, 89,550. Thank you. And then when I add them together, 100,000. Good. All right, so my standard divisor, is always your total population divided by the number of things you're apportioning, which in this case is 100 trucks. So that comes out to 1,000. So I divide each of my populations by 1,000, and I get 10.45 and 89.55 for a total of 100 trucks, right? But you can't send, 0.45 45 hundredths of a truck to one town and the other 55 hundredths to another town. So, so now I have to take my lower quotas, 10 and 89, and that adds up to 99. So I have one extra truck. And which town should get it? Southtown, because they have a larger decimal piece. They get the extra. So my final apportionment is going to be 10 trucks to Northtown and 90 trucks to Southtown, total of 100 trucks. Okay, feels completely reasonable so far, right? All right, so now the garbage company has just been hired by a third town, Easttown, that has 5,250 homes. So to accommodate the new town, the garbage company says, okay, well, we send about a truck per 1,000 people, right? So we'll buy 5 new trucks to accommodate this new town. And that means that service to the other towns shouldn't be affected. But when we carry out Hamilton's method with the additional town and the additional 5 trucks, now I have Northtown, Southtown, Easttown total. Didn't leave a lot of room there. And I have population, standard quotas, lower quotas, surplus, and final. Okay, so I have to get a new Well, I guess I can put in my populations. So the populations of the first two towns didn't change. So I have 10,450, 89,550, 5,250 for East Town, and then that should add up to 105,250. Which means now I'm going to have a new standard divisor because I have a new total population and a new total number of trucks. So my standard divisor is going to be 105,250 divided by 105 trucks now. And what does that come out to? 1,002.3. Okay. All right, so then I get my standard quotas by dividing each town's population by the standard divisor. So 10,450 divided by 1,002.3 is 10.42. And then 89,550 divided by 1,002.3 is 89.34. And 5,250 divided by 1,002.3, 5.24. Okay, so now I take my lower quotas. That should add up to exactly 105, or somewhere at least very, very close to 105. All right, and then I take my lower quotas, so I round everything down, and I get 10, 89, 5, and that adds up to 99 plus 5 is 104. I have one extra truck. Which town should I send it to? North Town. They have the largest decimal piece, so that's going to be 11, 89, 5. Oops, this is my surplus column. 1, 0, 0. And then my final is going to be 11, 89, 5 for 105. So what happened? Yeah, Northtown gave, Southtown lost a truck to Northtown. We gave Easttown its fair share of trucks, 5, exactly as we predicted, but then we switched to one from Southtown to Northtown, which feels a little bit like that irrelevant, independent of irrelevant alternatives from voting, right? So we had this weird thing happen where adding a new town with its fair share of trucks caused the apportionment for the other towns to change. And this is called the new states paradox. So, let's see, Southtown gave a truck or lost a truck to Northtown. Okay, so this result is called new states paradox. It happens when the addition of a new state, along with its fair share of seats, affects the apportionment of the other states. Okay, the other states seems like they should stay the same. Okay, so here's a little chapter summary. We learned 5 methods: Hamilton, Jefferson, Adams, Webster's, and Huntington Hill. And the only one that does not violate the quota rule is Hamilton's method, but it had these 3 weird paradoxes: Alabama paradox, population paradox, and new states paradox. And it tends to favor large states. Okay. Jefferson's method has upper quota rule violations, favors large states. Adams has lower quota violations, favors small states. Webster's and Huntington Hill can have both, though rare, upper and lower quota violations, but they're neutral. So it turns out that any apportionment method that does not violate the quota rule will produce paradoxes. And any paradox-free method will sometimes violate the quota rule. So this is called Belinsky and Young's impossibility theorem. So analogous to the Arrow's impossibility theorem from voting. So there is no perfect solution to the problem of apportionment. We just have better ones. Some are better than others. So what we do now is pretty good. So was Webster's. Pretty good. Now, before I let you go, there is a little helpful thing that we've come up with to help you remember which method is which. So Hamilton's method is the one with leftovers that you have to give out, right? So think of leftover ham. Yeah. You have to give out the leftover ham. So Hamilton's method, you can remember, oh, that's the one where I have leftovers to give away, right? All right, and then we have all the rest of them are modified divisor methods, and the only thing that's different is how you round, right? In the remaining 4 methods. So all the others are modified divisor methods. So those are ones where we change the divisor to make it so that there are no leftovers. The only difference is how you round. Okay. So in Adam's method, look at the first letter and it points up, right? So you round up. Right? In Adam's method, you always round up. And then in Jefferson's method, look at the first letter and it kind of points down, right? Round down. So Adam's method, it points up, you round up. Jefferson's method, it points down, you round down. And then Webster's method, in the first letter, the W points both up and down. So you round normal, right? Sometimes up, sometimes down, based on 0.5. Right? Sometimes up, sometimes down, round normally. And then for Huntington Hill, it is a modified divisor method, but the rounding is like this crazy rounding rule, right? That has to do with the geometric mean. So think Huntington Hill. Hill is kind of like, what the hell? What the hell kind of rounding rule is this? Okay? So that's how I remember it. Huntington Hill. What the hell kind of rounding rule is this? So that's the one where you round according to the brand new rule that has to do with the geometric mean. Any questions?